lithocap. At far southeast, FSE Lepanto in the Philippines. Why? Because silicic, the leaching that takes place at low pH is due to H plus chloride minus and H plus sulfate minus H1. Whereas over here, pH is greater than 2. Because over here, we have HCl. Here, the temperature is higher. This might be greater than 300 degrees, whereas this is less than 250 degrees. At high temperatures, acids are associated. Associado? They're HCl. But as the temperature decreases, the acids start to dissociate hydrogen and chloride. That dissociation, this is what is causing the reaction, the hydrogen ion. So that's why we get this lowest pH and the strongest leaching at lower temperatures. And at higher temperatures, we're left with alunite, other clays, graphite. Then what happens? What happens if we erode this? What's the most resistant? That is the erosion surface. But then, this is less resistant. So we get a case where the lithocap is first of all offset, plus it's higher. Just like this. Lithocaps, silicic lithocaps forming on the shoulder, not over the top of the porphyry. Now this is not always, but more and more we're finding evidence for offset. 500 meters, 1 kilometer, whatever distance. If you start drilling below the lithocap here, you're going to get propylitic, rootless, you think. But now this is the importance of alunite, 1480 nanometers, and Patricia will tell you about alunite. This is potassium alunite, whereas over here we have sodium alunite, approximately 1490 nanometers, and Patricia can identify that. Remember the coarse pink alunite we found? Here, that's 1482 nanometers. So that's relatively potassium rich. Now why? This is just empirical. We will look at this afternoon sometime. Well, basically, potassium alunite forms at lower temperatures. Sodium alunite forms at higher temperatures. And we can tell the composition from ASD. So that's one way to look at distal and proximal parts of lithocaps. At Lepanto, we see exactly this pattern. And so at least it will point us to the higher temperature end of the lithocap. And thinking about this, we want to focus our drilling not just also in the lithocap proximal, but maybe in the zone of, we need more colors here. What is, whoops. What is this zone?
That's the patchy.
Maybe what is patchy made up of?
De Pyrophyllite.
Pyrophyllite. So, if we have a lithocap with quartz alunite, and then we see on the edge of the lithocap there's a zone of pyrophyllite, well, that's the zone, the transitional zone. And what do you have here at La Reina? You have pyrophyllite in the transitional zone between Ethel and Calorca and the porphyry is a zone of pyrophyllite. Now we're going to discuss, there are two types of pyrophyllite. There's pyrophyllite that forms in this transitional zone, and then there's also other pyrophyllite that can form in the base of the lithocap. So we have to distinguish, because Patricia will just say, oh, it's pyrophyllite. But you, geologists, have to look at the context, the geologic context, to distinguish, is it pyrophyllite related to base of lithocap, high temperature, or is it pyrophyllite related to this transition? We'll be talking about this in more detail as we're going on, but these are good points. So what we're discussing is not academic, but it's to understand the fundamentals of zonation in a big system. We don't want to be drilling here, we want to be drilling proximally. ¿Tiene preguntas? No? Okay. And excellent.